Good afternoon. Thanks for attending this talk. Hope you guys are having a good time at the conference. It's always good to see so much activity on RISC-V. Today I'm going to talk about Ocelot, our open source vector unit. I am Srikanth Arekapudi. I'm the microarchitecture, RTL, and DV lead for all the CPU cores at Tenstorrent. Several engineers have contributed to this work, including DJ, who is the co-presenter in this talk. So here is the outline of the talk. I'm going to start off with talking about why we did this, and go over some implementation details of the vector unit, talk about why we chose Boom and Chipyard as core and integration environments, go over our open source verification kit, some performance results, and finally conclude the talk with some takeaways. So motivation. So at Tenstorrent, we design high-performing compute, which includes high-performing CPUs, high-performing AI accelerators, software stack to support that, and more. So when we started looking for ISA for CPUs, we looked at several of them, and then we actually stuck with RISC-V for the same exact reasons several people have talked throughout the conference. So I'm not going to go over those. I think we know all the good things about RISC-V. So, and then the vector extension for RISC-V is rich and huge. So when we talked about doing a high-performing vector extension or vector unit, we looked at the instruction set, and it was a daunting task to just do it from the get-go because of the number of instructions, and then we're starting from scratch, trying to build the verification environment and design and everything. So instead, we said, hey, let's start with a simple, fully functional RISC-V 1.0 compliant vector unit that can be used as a reference platform for our future designs, also can be used for software bring-up. So when we started the RISC-V design, we started using a lot of open source components. I mean, it was kind of easy to start on the RISC-V designs because of so much activity going on in the open source, thanks to all of them who contributed to that. Then when we were actually done with this design of this vector unit, we thought, hey, we use so much of open source, so let's also give it back to the community and be engaged with it. So that's one of the reasons for the open source. And also we thought it will speed up the vector adoption. And it was our way of engaging with the community. So we have also done some performance benchmarking. That's our way of understanding how the ISA is and trying to, again, pave our way towards building higher performing vector units. So the other thing I want to add here, generally on behalf of Tenstorrent, is you guys might have attended my colleague Vehan's talk today. He talked a lot about what we do at Tenstorrent. If you haven't, I strongly encourage you guys to kind of take a look at the talk when it becomes available online. So just wanted to go over some specs on the vector unit. The intent was to build a RISC-V 1.0 compliant vector unit. Most of the code is written in System Verilog, some in Chisel. Some of you might be familiar with Chisel. And we support vector lengths of 128, 256, 512. SEW 8, 16, 32, and 64 with half precision, single precision, and double precision support. We use Hartford library. I was talking to John yesterday. He's here, thanking him for the library because that was a quick way for us to get started, designing or using the floating point without having too much floating point expertise. So we implemented almost all the instructions. A couple of instructions we're still working on, haven't implemented yet, are the divide, remainder, and the square root. Currently, the integer supports round to nearest up only, and exceptions are only supported in software. So with that, I want to kind of dive into some of the implementation details of the vector. Like I mentioned earlier, it's a simple vector design. Starting with issue of the instructions. If the instructions have dependencies on integer or floating point registers, we read them. The hard float uses a format called REC-FN, which is different from the IEEE floating point. So we have a conversion between the IEEE floating point and the REC-FN formats. And then we write to, once we have all the operands ready from the integer and the floating point side, not the vector ones, we write to the request queue. So this request queue is a queue of vector instructions. It gets drained in order. Once we pick an instruction from the request queue in order, we start decoding. A couple of things I want to talk about. The decode is, it's kind of straightforward, but not exactly straightforward, because vector has, vector unit, vector ISA has elmos. Each instruction can be decoded into one operation or several operations. For example, if elmol is 1, it's one operation. Elmol could be up to 8. So the decoder kind of works as a sequencer also. So once we actually go through the sequence, we pick an operation. We read the vector registers for the operation. If the operation is a load store operation, we do an address generation, and then we write it to the result tracking buffer. I just want to take a minute and talk about the result tracking buffer. The result tracking buffer keeps track of all the operations waiting for a result. For example, if you have a load, it might be hit in the cache, takes a couple of cycles. If it's a miss, takes several cycles. We reserve an entry in the result tracking buffer. If the result tracking buffer is full, obviously we stall all the way to the back. But till we receive that result, the op stays in the result tracking buffer. Once we get the result and the op becomes the oldest, then we deallocate from the result tracking buffer. So once we actually have the load in the result tracking buffer, we actually go check whether it's in the D-cache. If it's there, we get the data back. If not, got to fetch far away. And then write the result back to the result tracking buffer, wait for it to become the oldest op, and then write back to the register file. So it's a pretty straightforward and simple design. Similarly, if the operations are vector arithmetic instructions in our implementation, depending on the operation, can take single cycle, 2 cycles, 3 cycles, or more than 3 cycles. I have a table later talking about that a little bit. Same thing here. When the vector operation is done in the data path, we actually write the result to the result tracking buffer, and then from there, we actually write it back to the register file once the operation becomes the oldest in the result tracking buffer. Just want to go over a little bit on the FP data path. The data is always sourced from the register file. Sorry, one thing I forgot to mention earlier was there is no data forwarding. The data always gets written to the register file and gets read from the register file. And the FP compute, like I mentioned earlier, was hard float. Have a reference there from John's work. The encoder shown here does convert the IEEE floating point format to the REC-FN format. It also does the operand widening. So once that is done, our data paths for half precision, single precision, and double precision are separate. Like there are 3 independent data paths, although at a given time, we only have one operation going through. I'll talk about that a little bit. And we designed this as 4 separate lanes. For example, here, the picture here is showing a 256-bit data path for a VLAN of 256. So each lane has 64, max 64 bits, so that we need 4 lanes. If it was 128 VLAN, we would have 2 lanes. If it is 512, we'll have 8 lanes. Once we are done with the operation, we have to, what's not shown in the picture is there is a mux, which actually mux between, whether it's 16, 32, or 64, and then we actually do a format conversion, and then write back to the register file. So currently, the vector unit only supports single load store pipe. So one other thing I want to mention, maybe better to go back to the previous slide, is when the operations are, we do support different latency operations to go through at the same time. For example, you can have a single cycle, a 2 cycle, and a 3 cycle, not in the same cycle, but the results can be written in the same cycle. So the result tracking buffer has 3 writes. And we figured out with a combination of 1, 2, 3, we can fit in the rest of the combination. So, so we do support that. It's not, at least we don't stall it when there is a result contention. Okay, good. So this is a table showing the data path latencies. Just to explain what this table is, the left column is the category of the instructions. The second column is the sample instructions from that category, and the third section talks about different SEWs, 8, 16, 32, and 64. I'm going to just read through it, but the basic integer and FT converter operations take single cycle in the data path. This is the latency of the data path. And the complex integer, narrowing, floating point add mul, FMA take 2. The widening, floating point integer take 3. I think the rest of the operations take more than that. We haven't really optimized for the reduce and gather slide yet. So now that we have talked about the vector unit, I want to kind of talk about why we chose Boom and Chipyard. The vector unit is designed to be standalone. So you could take the vector unit, which is open source. We open source the integration with the Boom and Chipyard also. But you could take vector unit standalone and can use it with any core. For us, when we wanted to run more tests, we are looking for a core to integrate it with. Since our intent was to eventually design a higher performing vector unit, this was basically done as the first pass initial design. We chose Boom. Boom is an out-of-order machine, decently performing. So we thought it's going to be a good platform for us to start integrating the vector unit. And eventually, when we actually go ahead and design a better one, we are already used to the out-of-order core here, so it's going to work better. And Chipyard mainly because it's a rich environment. I mean, it has a lot of stuff already. We can do a lot of simulations. It provides an emulation platform through FireSim for FPGAs. It has ready-to-integrate path for software. So, and a lot of IPs, Boom, Rocket, other cores in there. So that's kind of our main motivation. And the picture on the right kind of shows, very simple, top-level diagram of how we integrated it. We take the decoder instruction. I think write it into the issue queue. And the vector pipeline is something I talked about in the previous slides. There is a vector config space. We have a single load store that the vector unit supports. It kind of gets stitched into the load store unit of the Boom core. So now that we have talked about the vector unit and the integration with the Boom and Chipyard, I want to go over our verification. So the main focus here was to verify the ISA. That's the primary intent for us to implement a simple vector unit and then just go through all the instructions, verify it, trying to understand more of the instruction set. So 3 components we already released to open source. The first one is TT Whisper. It's our in-house instruction set simulator. Can be configured with a JSON file, and we can tell it what to exclude in different ways. The second component is the core verification kit, which can do instruction by instruction checking between Ocelot, which is our vector unit, to TT Whisper. By the way, not only that, you could probably integrate this with something else also, but the TT Whisper provides that capability. We have even done the FireSim FPGA emulation on this in a COSIM mode. So even that, we can actually check instruction by instruction. The third portion is the self-checking assembly test, which we thought is very important, because then you could, changes are made, you could always run through the self-checking assembly test, to iterate through various configurations and instructions of the ISA. So for future work, we are working on more, open sourcing more on some architectural coverage, micro-architectural vector cracking, vector instruction cracking. With that, I'm going to move on to some performance numbers. We haven't done tons and tons of work on this, but we just done some basic work to understand where we stand. We already know the bottlenecks in the vector unit when we implemented it, and we chose to do it that way for simplicity. But these are, providing us more insights and proving to us what we kind of expect to see. So again, explaining the table, the left column talks about the applications kernels like arithmetic mean, AXPY, inner product, ReLU, matrix multiplication, transpose, convolution, 1D and 2D. The second section talks about the dynamic instruction count. This is pretty much the instruction count you see in assembly or the instructions you commit. So within that, there is a scalar. The same code, if you run with scalar mode, how many dynamic instructions would you see versus enabling the vector extension? So the vector extension enabled, I want to talk a little bit on this also. There are two ways we did this. We actually tried to use the auto vectorization of LLVM. So we took the same code that we ran on the scalar with the scalar mode. We actually turned on the auto vectorization with LLVM and ran it. So it does. So believe me or not, there are couple of things here where our initial handwritten version was worse than the auto vectorization. But it only did it for a couple. So I want to give the credit. But there are more where it wasn't doing a better job. So we had to do intrinsic handwritten code. So this is kind of like, think of it as a best of both, right? Whatever we could. I mean, if auto vectorization was giving us a better, we didn't want to like go dig into and write more. And then the ratio is showing basically what is the ratio of the instructions. I mean, ideally you would expect the ratio to be showing on the other side too in a performance improvement. The third section is talking about the cycle count, which is basically the actual time taken to run these. So the instruction count doesn't mean something is faster than the other, because the vector unit, like we talked about, it has its own pros and cons. So the cycle count shows, I mean, you can see the ratios of the instruction count, and then when you go to the cycle count, yes, enabling the vector extension still is better. But like I said, it's a simple vector design to start with, it's the first version. So just even getting these numbers is a good thing to start. So there is more work to be done, which I'm going to talk in the next slide. Just wanted to point out, all these results are measured with the small configuration of the boom with a VLAN of 256. Okay, so now finally getting to the takeaways. So performance trade-offs. Today, we don't support even the unit stride vector load stores internally get broken down per element. So if you have 16 element based load store, it takes 16 operations, 16 loads. So it's not optimized at this point. And then the other thing on the store queue side is, because we stitched the vector unit into the boom, we don't have a better way of allocating store queue entries. We rather allocate one store queue entry for the entire instruction, and then basically and then we cycle through each element, and then we just use the same store queue entry. I mean, we just figured out a backdoor way of doing this quickly. But we see that in the results. Like, for example, if we fix these, the results would have been different. And the other thing I want to point out is the VL. I mean, this is an in-order simple vector unit. There's no renaming on the VL, and that actually also causes a lot of serialization. So basically, what we do with the vset VLI instructions right now is we basically write the VL to a CSR and then wait for the CSR to be updated before we issue any of the dependent instructions. So we pretty much stall the machine if you see the vset VLI. So, and then, to add to it, I want to put some more points on the future improvements. We can enable bulk memory accesses, like especially for the unit stride, not too hard. I mean, if you are actually talking about indexed load store, definitely it's still more work to have any sort of bulk memory accesses, but unit stride is pretty straightforward. And then we have done some preliminary work, which I'm not showing here, but we already saw just by doing unit stride bulk memory accesses, the performance can go 2x or more. I mean, it was average was 2x. Some cases it was a lot more, some cases it was slightly less. And we wanted to, the future work, we wanted to add support for exceptions, add support for out-of-order execution and register renaming, which obviously was not present at this point. And we wanted to add support for indexed ordered segment load store. Okay, so with that, I want to kind of conclude my talk with our open source collateral. Earlier in the talk, I thanked the open source community, and there's a lot of stuff we have used, and this is all from us. We have the Ocelot, which is the presentation today. We actually have the instruction set simulator, TT Whisper. We have the DV kit. We have the vector test. We have the arc checker and stimulus, also open source from our side. That concludes my talk. Thank you so much.
All right, let's give him a hand. I do have one question that came in online. We'll start there because it's the first question I've received all day online, so we're going to give them credit.
Thank you.
Without revealing your process technology, what is the frequency target for Ocelot?
So we were somewhere around 1 to 1.2 in a fairly new node.
Okay.
But I have to say that we haven't really tried to productize this vector unit. So this is our basic initial runs.
All right. I'll take one question from the audience. Alan, I'm going to skip you. I'm sorry. I saw Bilal first. You're going to get a little exercise. Last question for this topic. Bilal, make it great.
Sure. Maybe Alan had the same question. Is there any plan to release the assembly code for the tests, or we'll have?
Sorry, can you repeat the question again?
So the tests you have released are released in ELF form. There's no assembly.
I think we have. I think Divyang is here from our team. He can comment a little bit more on that.
Oh, here we go. Yeah, now we have an answer from the audience. This is great.
Yeah, so yeah, at some point we will, but you could just disassemble the ELF file and just get information out. One of the challenges there is it's got a lot of custom code that we wrote that refers to other related items. So we're not able to do it right away, but you should be able to disassemble it. Yeah.
All right, let's give them one more round of applause and thank them for their effort and a wonderful topic.
Thank you, guys.